Hello, my name is Repai, DE200117. So I'm going to present to you for our project title, which is the simulation of different types of faults and their detection for coarse power system protection. We are from Group 5, Section 1. So here are our group members. First we have Aliah Farisyah. Next is Recher, Norsafirah, Tommy, and also Amiruddin. So as for the introduction, a fault in the power system can be caused by various factors such as short circuits, installation failure, equipment malfunctions, or external events like lightning strikes. So these faults can disrupt the normal operation of the power system, and it can cause damage to equipment and potentially lead to blackouts or other safety hazards. The primary goals of fault protection are to minimize the impact of faults and restore the power system to a stable and safe condition as quickly as possible. And in order to achieve this, the several protective devices, schemes, and coordination techniques are used to prepare the power system to face with different types of faults that can be unpredictable. For example, by designing a fault protection scheme, which requires a thorough analysis of the power system characteristics, including its topology, load requirements, fault levels, and also equipment ratings, and overall real-life power systems fault protection and project scheme design aim to ensure the reliability, safety, and efficient operation of the electrical power system. Thank you.
Okay, my name is Nurul binti Halim. My matrix number is DE200118. So today I'll be presenting the literature review for this project. So for the types of fault, there are 4 types of fault that can be gathered in this project, which are short circuit fault, open circuit fault, ground fault, and over voltage and under voltage fault. For the short circuit fault, it can be categorized into 3 parts, which are single line to ground, line to line, and line to ground, or as we know as double line to ground. These faults were brought on by conductors' contact with the earth. For open circuit fault, there are 2 types of fault that can occur based on this type of fault, which are open conductor fault and open transformer winding. These fault occur when the link is lost or detached from one another. For ground fault, it can be detected based on the impedance level served as the basis of the issue, which can be seen as high impedance fault and low impedance fault. For over voltage and under voltage, it can be seen from the voltage level found on the line served as the basis for this issue. So for the fault detection method can be categorized based on the type of fault that we gathered. So for detection method of short circuit fault, it can be detected using overcurrent relay, differential relay, and zero sequence current detection. For open circuit fault, it can be detected using impedance monitoring and monitoring for loss of voltage or current. Based on this monitoring, there will be a noticeable drop in or absence of the corresponding quantity. So for the ground fault can be detected using ground fault relay and natural grounding resistor. Lastly, for the over voltage and under voltage fault, it can be detected using voltage relay and under or over voltage protection devices. I'll pass this presentation to my next team member.
Hi, my name is Liang. So now I'm going to demonstrate the simulation that we have already done in the project. So this is in MATLAB Simulink. So this is the block model of the simulations. So we have 3-phase source here connecting to a 3-phase breaker, and this is for the measurement. So this is the fault block that we use to insert the fault into the system. So this is the load, and this is a logic subsystem to control the breaker. So this is just scope to take the measurement. So for the first one, we want to see the result for the normal operating of this system without fault. So just untick this fault between each phase, apply, then we try to run. So this is the result of the normal operating of the system. So as we can see, this is the source voltage, three phase. It is equal from each other, and this is the source current, load voltage, and load current. So we can observe that the source voltage is equal, same with the load voltage, and same also for the current. So for the first case, it is between phase A and ground to simulate a single line to ground fault. So we apply, and now we try to run again. So as you can see here, so this is the source voltage. So during the fault at 0.025 seconds, so the voltage drop until 0 for a period of time. So this is the source current. So as we can see, this is the fault current, very high here, and this is the low voltage. So for the low voltage, because of the fault during this time, the fault period, so the voltage will be cut off. Same also for the load current. So during that time, the breaker will cut off the connection to the load from the source. So as we can see here, it is 0 for only one phase because it is single phase to ground, single line to ground. So same, if for the second case, it is double line to ground. So we tick between phase A and phase B and the ground. So apply, and now try to run again. So this is the result as we can see. So for the source voltage, we have two phase A and B is 0 during the for period 0.025. So this is the fault current for phase A and phase B. So as we can see here, it is very high. So for the load voltage, it is same as previous case. So the breaker will cut off the connection to the load. So at the load, if we measure, there will be no voltage here, and there will be also no current during the fault period. So for the third case, it is between only phase A and phase B to demonstrate the line-to-line fault. So this is the result for the third case of line-to-line fault. So as we can see, this is the source voltage after the phase A and phase B directly contact. So this is the source voltage, and this is the fault current. So as we can see here, the magnitude of the current in source of phase A and phase B is same but in opposite directions. So they will cancel out each other. And as we can see here, there will be also voltage and current in the load because of the fault current is cancelled out by each other. So the breaker will not totally shut down the connection to the load, but the voltage and the current in the load is a little bit smaller compared to the normal current and voltage in phase C. So for the last case, it is between phase A, phase B, and phase C to simulate the three-phase fault. Okay, so this is the result. So as we can see, this is the source voltage. So when the three phase is directly contact in between each other, so the voltage will be 0 for three phase, and the fault current is here. We can see it is very high and is very messy between the three phase in the system. So for the load voltage, so the breaker will eliminate the connection between source and load, and so therefore we will see 0 here, 0 voltage during the fault period. And for the current, it is also the same because of the breaker already cut off the connections, so there will be 0 current in the to the load during the fault period. So that's all for the simulation and the result sharing. So thank you. I will pass the next presentation to my friends.
Hi, Assalamualaikum. My name is Norsafirah binti Ishak. My number matric is DE200066. I will talk about the result and discussion for this project. So as we can see here is normal operation of our system. And this section, the sources voltage supplied by the sources will be similar with the load voltage received by the load in the power system. The same theory is applied to the current in the power system because there is no fault that detected in the power system. And for the normal operating, the source phase voltage of VA, VB, and VC is equal to 14.43 kV, while sources phase current of IA, IB, and IC is 141.42 ampere. And the breaker will keep closed as there are no trigger signal to open the breaker during the operating condition. There are 4 fault conditions to be tested in this system to observe the effect of each fault toward the power system, which are single line to ground fault, double line to ground faults, line to line faults, and 3-phase fault. For the single line to ground fault, phase A, as we can see in the figures, phase A is connected to the ground in the fault block to replicate the situation. It's been observed that before t equal to 0.025 second, the system operates normally in steady state condition, and when the phase A is grounded during the result shown, the sources voltage of phase A drops approximately to 0 in a short time, while the source current in phase A start to increase gradually due to the fault current. The source voltage and current in phase B and C not affected by the fault and operate normally. When the current breaker detected the fault in phase A, it will trigger and cut off the supply to load A. It can be observed in the load voltage and load current in this figure, where at the t is equal to 0.025 second, the load A is not receiving any supply due to the breaker has isolate the fault from the load to prevent the high magnitude of fault current fed into the load. The breaker will be closed again to connecting the sources to the load after the fault current is to appear once the fault is eliminated at t equal to 0.05 second. Next, for the double line to ground fault, as shown in the figures, phase A and phase B is connected to the ground in the fault block. The system is operated normally before the fault occurs at t is equal to 0.025 second. The sources current in both phases start to become unstable with high magnitude, and the sources current at the same time of the fault occurred, the overcurrent will detect the high fault current in the system and cut off the supply to be a load in phase B and C. Both phase B and C have 0 voltage and 0 current starting at the t is equal to 0.025 second. Once the fault current is eliminated, the breaker will continue connect to the supply to the load at both phases. For line-to-line fault, phase A and phase B is chosen to be get in contact and create a low resistance path between both phases during t is equal 0.025 seconds, and the source voltage of phase A and B become half of the voltage level in phase C due to the voltage is summed up together. Due to the fault current in phase A and B is same in magnitude but in opposite to each other, the fault occur will cancel each other to form 0 fault current in the system. The breaker will not cut off the system, but in the result, the load current for phase A and B is lowered compared to the normal phase C. The load voltage is same with the result of source voltage, only the magnitude in phase is different due to the fault. Lastly is the 3-phase fault, where is the fault current in the system will be very huge during the fault at t equal to 0.025 second, and before the fault occur, 3-phase in the system just operated normally. The source voltage for 3-phase will drop to 0 as the source's current is very high. Once the breaker detected the huge fault current in the system, it will immediately cut off the connection to the load for 3 phases. The load voltage is same with the result of source's voltage. Only the magnitude in phase is different due to the fault. The load will be disconnected from the voltage and current sources starting from t equal to 0.025 second until the fault current is eliminated from the system. I think that's all from me. Thank you.
Hi, my name is Muhammad Amiruddin Hasrolnizam, DE 200-123. So for the conclusion for our project, the result obtained in MATLAB Simulink on the simulation of different types of faults and their detection in the power system shows that the overcurrent circuit breaker able to deal with different kind of faults in the power system. As the example, when single line to ground fault occurred in the power system, the circuit breaker able to isolate or cut off only the faulty phase while keep the other phases with their normal operation. Besides, by using the simulation, the overall performance of the power system in regard of the voltage current during fault occur is successfully to be simulated and observed by the output graph. The simulation can provide insight to the power system performance during fault, and the suitable protective scheme can be included into the system to improve the reliability and the efficiency of the system. So that's all from our group. Thank you.